C# and AI Masterclass by Edgar Milvis Volume 9, Chapter 14. Let's discuss Chapter 14, Text-to-Speech, TTS, with local models. Turning our attention to theoretical foundations. The transition from processing text to generating human-like speech represents a fundamental shift in how applications interact with users. While local large language models, LLMs, like Phi or Llama excel at understanding and generating text, they remain silent, literally. To bridge this gap, we implement text-to-speech, TTS, systems that run entirely on the edge, ensuring privacy, low latency, and offline capability. This section dissects the theoretical architecture of local TTS, focusing on the conversion of text into acoustic features and subsequently into raw audio waveforms using the ONNX Runtime within a C# environment. Now, let's explore the TTS pipeline, a multi-stage transformation. At its core, a modern TTS system is not a single monolithic model but a pipeline of specialized components. Unlike older concatenative methods that stitch together pre-recorded phonemes, modern neural TTS utilizes a sequence-to-sequence approach. The process generally follows this flow. 1. Text normalization and tokenization. Raw text is cleaned and converted into a sequence of phonemes or characters. 2. Acoustic model, text-to-spectrogram. This model, often based on architectures like fast speech or VITS, converts the token sequence into a visual representation of sound, the spectrogram. 3. Vocoder, spectrogram to waveform. This model takes the abstract spectrogram and reconstructs the raw audio waveform, the actual sound waves. Now, let's explore analogy, the architect and the builder. Imagine constructing a building. The acoustic model acts as the architect. It takes the blueprint, the text, and creates a detailed schematic diagram, the spectrogram. This diagram doesn't look like a building, it shows the structure, the height of the walls, and the placement of windows, but it is abstract. The vocoder is the master builder. It looks at the schematic and uses physical materials, mathematical synthesis, to construct the actual physical building, the audio waveform. One cannot exist without the other if you want a functional result. Let's discuss Deep Dive 1, the acoustic model, the architect. In the context of local TTS, we often utilize models like Piper or VITS, variational inference with adversarial learning for end-to-end text-to-speech. These models are typically trained on massive datasets of audio and text pairs. Now, let's talk about the spectrogram, visualizing sound. Before understanding the model, we must understand its output, the MEL spectrogram. Sound is a wave. In a digital system, we represent it as a sequence of amplitude values over time, the waveform. However, raw waveforms are high-dimensional and noisy for a neural network to process directly. A spectrogram breaks the audio into short time windows and analyzes the frequency content of each window. A MEL spectrogram is a variation where the frequency axis is converted to the MEL scale, which mimics human hearing sensitivity. We perceive lower frequencies better than higher ones. To a neural network, a MEL spectrogram looks like an image. The horizontal axis is time, and the vertical axis is frequency intensity. Why is this critical for C# developers? When we load these models in ONNX Runtime, we are not dealing with audio initially. We are dealing with tensors of floating point numbers representing this spectral image. In C#, we manage these tensors using the Microsoft.ml.onx runtime library. The input to the TTS model is a tensor of integers, text tokens, and the output is a 3D tensor representing the MEL spectrogram, batch size times MEL channels times time frames. Turning our attention to the architecture, VITS and monotonic alignment. Models like VITS utilize a variational autoencoder, VAE, combined with normalizing flows. Without getting lost in the calculus, the goal is to map the discrete text input to a continuous latent space that represents speech. A critical concept here is monotonic alignment search, MAS. When we speak, the timing of phonemes is rigid, hello always flows in a specific order. The acoustic model must learn this alignment without explicit timing labels during training. It ensures that as the text tokens progress, the corresponding audio frames progress linearly. In C#, when we invoke the inference session for the acoustic model, we are essentially asking the model, given this sequence of token IDs, generate the sequence of MEL frames that statistically resemble the training data of a human voice. Now, let's talk about Deep Dive 2, the vocoder, the builder. The spectrogram generated by the acoustic model is a magnitude representation. It lacks phase information, the shape of the wave. Converting a spectrogram back to audio is an ill-posed problem. There are infinite possible phase configurations that result in the same magnitude. Modern vocoders, such as Hi-Fi GAN, often used with Piper, are generative adversarial networks, GANs. They are trained to generate waveforms that are indistinguishable from real audio. Now, let's explore how HiFiGen works. HiFiGen uses a generator to create audio from the spectrogram and a discriminator to judge if the audio is real or fake. The generator learns to upsample the spectrogram, which has a low time resolution, to the high-resolution audio waveform, typically 22,050 Hz or 44,100 Hz. The C# implication: this is computationally expensive. Generating audio frame by frame in real time requires efficient memory management. In C#, we cannot afford to allocate massive arrays on the heap for every millisecond of audio. We must use span T and memory T to manage buffers for the audio chunks. Furthermore, the vocoder takes the MEL spectrogram tensor and outputs a raw audio tensor, 1D array of floats. This raw audio must be converted to a standard format, like PCM 16-bit, to be playable. Turning our attention to theoretical foundations. The beauty of using ONNX, Open Neural Network Exchange, is hardware abstraction. Whether you are running on an Intel CPU, an AMD GPU, or an ARM-based Raspberry Pi, the ONNX Runtime optimizes the execution graph. Now, let's explore the execution graph. When we load a TTS model in C#, we are loading a directed acyclic graph, DAG. Each node in the graph represents an operation, e.g., matrix multiplication, layer normalization, convolution. The diagram illustrates the sequence of fundamental neural network operations: matrix multiplication, layer normalization, and convolution, processing input data to generate an output feature map. Let's discuss memory management and async/await. TTS inference is blocking by nature, math takes time. However, in a responsive UI or a server application, we cannot freeze the main thread while the GPU crunches numbers. This is where C#'s async and await keywords become architectural pillars. We wrap the ONNX inference calls in task, run, or use the native async capabilities of the ONNX runtime, if supported by the execution provider. This allows the application to remain responsive while the architect and builder are working in the background. Moving on to real-world analogy, the orchestra conductor. Think of the TTS system as an orchestra. The text, the musical score. The acoustic model, VITS the conductor. They don't play an instrument but dictate the tempo, volume, and pitch, the spectrogram, for every section. The vocoder, HiFiGen the musicians. They take the conductor's abstract directions and produce the actual sound waves from their instruments. In our C# application, the ONNX session object is the stage manager. It loads the sheet music, the .onx file, allocates the rehearsal space, memory buffers, and ensures the conductor and musician stay in sync, tensor shapes and dimensions. Turning our attention to edge cases and nuances. 1. Voice conditioning. Speaker embeddings. Many local TTS models support multiple voices. This is handled via speaker embeddings, vectors of floats. In the C# implementation, we must manage these embeddings as additional inputs to the ONNX graph. If the tensor shape does not match the expected embedding dimension, e.g., 256 floats, the inference will fail. Concept reference. As discussed in Book 8, Chapter 12 regarding vector databases, we treat these embeddings similarly, static vectors that modify the context of the inference. 2. Length scales and noise. Neural networks are sensitive to input scaling. The acoustic model outputs a spectrogram with a specific time dimension. If the text is long, the time dimension grows. The vocoder must handle variable length inputs. In C#, this means we cannot pre-allocate fixed-size arrays. We must use dynamic lists or resizable spans, carefully managing the heap allocations to prevent garbage collection, GC, spikes, which would cause audio stuttering. 3. Streaming versus batch. For real-time conversation, like the LLM chatbots in previous chapters, waiting for the full text to be generated before starting TTS introduces unacceptable latency. Strategy. We implement streaming TTS. As the LLM generates text chunks, we send them to the TTS pipeline immediately. C# feature. We use system, threading, channels or async enumerable T to create a producer/consumer pipeline. The LLM produces text tokens, producer, and the TTS system consumes them to generate audio chunks, consumer. This decouples the generation speed from the playback speed. Moving on to the role of modern C# features. To build a robust local TTS system, we leverage specific C# capabilities, refstruct and span T when processing raw audio buffers, converting float arrays to byte arrays for playback. Using span T allows us to work with stack-allocated memory or shared memory slices, avoiding heap allocations entirely. This is vital for high-frequency audio processing loops. Record types. For configuration management, e.g., record TTS config, string model path, int sample rate, float length scale, records provide immutability and value semantics, ensuring that configuration changes propagate predictably through the pipeline. Dependency injection, DI. We abstract the TTS engine behind an interface, just as we did with the LLMs. Here we're defining a C# interface named ITTS engine. In object-oriented design, an interface serves as a contract, outlining a set of methods that a class must implement if it chooses to adhere to this contract. Think of it as a blueprint for behavior, not an implementation itself. This abstraction is crucial for building flexible and maintainable systems. By defining ITTS engine, we're saying that any component responsible for text-to-speech, TTS, synthesis in our application must provide a specific method to perform that task. This allows us to swap out different TTS implementations, e.g., one based on ONNX, another using a cloud API, without changing the core logic of the components that use the TTS engine. This is a prime example of the dependency inversion principle, a cornerstone of solid design, promoting loose coupling. This allows us to swap between a high-quality but slow vocoder and a faster but lower-quality one based on the device capabilities, e.g., desktop versus mobile edge device. Moving on to theoretical foundations. 1. Input, a string of text enters the C# application. 2. Tokenization, the text is converted into a sequence of integers, tokens, using a phonemizer. 3. Acoustic inference, the tokens are passed to the ONNX acoustic model. The runtime executes the graph, producing a MEL spectrogram tensor. 4. Vocoder inference, the spectrogram tensor is passed to the ONNX vocoder model. The runtime executes the upsampling graph, producing a raw audio tensor, floats. 5. Post-processing, the float audio is converted to PCM 16-bit integers, standard audio format. 6. Playback, the PCM data is fed into an audio buffer, e.g., waveout event in NAudio, for real-time playback. By understanding this pipeline, we move beyond simple API calls and gain full control over the speech synthesis process, enabling us to create truly private, offline, and responsive voice-enabled applications. Now, let's talk about basic code example. Here is a self-contained, hello world level example of running a text-to-speech, TTS, model locally using C# and ONNX Runtime. This example simulates the core logic of a TTS pipeline, converting a text string into a sequence of audio tokens, acoustic features, and then synthesizing those tokens into a raw audio waveform using a vocoder. Moving on to prerequisites. To run this code, you need the ONNX Runtime NuGet package. You can install it via the .NET CLI. This line isn't C# code in the traditional sense, it's a .NET CLI command. It instructs the .NET SDK to add a NuGet package named Microsoft.ml.ONNX Runtime to our project. In essence, we're telling our application, hey, we need the ONNX Runtime library to execute ONNX models. This is a crucial first step for any project that aims to leverage ONNX for machine learning inference, as it provides the core functionalities for loading, parsing, and running ONNX-formatted deep learning models efficiently. Without this package, our C# application would have no way to interact with or execute the ONNX models that are central to local inference and edge AI. Moving on to the code example. This example uses a mock TTS model and a vocoder model to demonstrate the pipeline. In a real-world scenario, you would download pre-trained ONNX models, like Piper or VITS, and replace the dummy inference logic with actual inference session, run, calls. Here, we're bringing in essential namespaces from the .NET framework. Notice Microsoft.ml.ONNX Runtime and Microsoft.ml.ONNX Runtime, tensors. These are crucial because they provide the capabilities to load, run, and interact with ONNX, Open Neural Network Exchange, models. ONNX is an open standard for representing machine learning models, allowing us to run models trained in frameworks like PyTorch or TensorFlow directly within our C# application. This is a cornerstone for local inference, as it decouples the model training environment from the deployment environment. We start by defining our local TTS demo namespace, which helps organize our code and prevent naming conflicts. Inside, the program class contains our main method, the entry point for our console application. At line 14, we declare a simple text input string. This is the text we want our text-to-speech, TTS, system to convert into audio. This initial step simulates the user providing input to our system. This section introduces the first major step in a TTS pipeline, tokenization. At line 19, we call tokenize text. In a real-world scenario, this isn't just splitting words, it often involves converting text into phonemes, the distinct units of sound in a language, or subword units using complex tokenization models, e.g., BPE, word piece. The output, token IDs, is a sequence of numerical representations that the acoustic model can understand. This abstraction is vital because neural networks operate on numbers, not raw text. Next, we move to the heart of the TTS system, the acoustic model inference, initiated by run acoustic model at line 24. This model takes the token IDs and transforms them into a MEL spectrogram. A MEL spectrogram is a visual representation of the sound's frequency content over time, perceived on a MEL scale, which is closer to how humans hear. This is a compact, rich representation of sound, capturing the what and when of the speech without explicitly defining the how, which is the vocoder's job. Models like VITS or Tachytron are examples of such acoustic models. Following the acoustic model, we have the vocoder inference, handled by run vocoder at line 29. The vocoder's role is to convert the MEL spectrogram, the acoustic features, back into a raw audio waveform, a sequence of amplitude values over time. This is the synthesis part, turning abstract features into audible sound. Models like WaveNet, WaveRNN, or HiFi-JN are popular vocoders. This two-stage approach, acoustic model plus vocoder, is common in modern TTS, allowing for modularity and often better quality than end-to-end models, especially for local inference where model sizes might be a concern. Finally, after generating the audio waveform, we simulate saving it to a file using Save Audio to File at line 34. In a production application, this would involve writing a proper WAV file header and then the raw audio samples. For this demonstration, we're just acknowledging that the audio data has been produced and would typically be persisted or played back. This step completes the full text-to-speech pipeline. Now we dive into the tokenized text method, which is the first functional block of our TTS pipeline. At line 41, we explicitly state that this is a simulation. In a real-world scenario, this method would not just map characters, it would likely involve a sophisticated phonemizer or a pre-trained tokenizer model, potentially an ONNX model itself, that converts text into a sequence of phoneme IDs or subword tokens. This is crucial for handling pronunciation nuances, different languages, and out-of-vocabulary words. The loop from lines 45 to 50 demonstrates a very basic character-to-ID mapping. We convert the input to lowercase for consistency, then assign arbitrary integer IDs, AZ get 1 to 26, space gets 27, and punctuation gets 28. This simple mapping serves as a placeholder. The choice of token IDs and their mapping to actual sounds is determined by the specific acoustic model being used. A more advanced tokenizer would handle capitalization, numbers, abbreviations, and complex linguistic rules to ensure accurate pronunciation. Here we begin the run acoustic model method. Notice the commented out line 59, var session equals new inference session, TTS_model.onx. This is a critical hint. In a real application, this is where we would load our pre-trained acoustic model, which would be an ONNX file. Inference session from Microsoft.ml.onx runtime is the gateway to running these models. The model file encapsulates the neural network architecture and its learned weights, ready for inference. For this demo, we're simulating the output of such a model. At lines 61 to 64, we create a dense tensor float named input tensor. This is how ONNX Runtime expects numerical input for models. We define its shape as 1, token IDs, count, representing a batch size of 1, a single input text, and a sequence length equal to the number of tokens. We then populate this tensor with our dummy token IDs. This step is fundamental. It correctly formats the input data into the multidimensional array structure, tensor, that the ONNX model is designed to process. Incorrect tensor shapes or data types would lead to inference errors. The commented out lines 67 to 70 show the actual ONNX inference process. We would create a list of named onx value objects, associating our input tensor with the input name expected by the ONNX model, e.g., input. Then, session, run, inputs, would execute the neural network, and results, first, .astinsert float, would extract the output tensor. This is where the model's intelligence would transform the token IDs into acoustic features. We're skipping this for simplicity in the demo, but it's the core of using ONNX Runtime. Since we're simulating, we need to generate a mock MEL spectrogram at line 72. We define its target shape, 1, MEL channels, time steps. MEL channels, e.g., 80, represents the number of frequency bins in our spectrogram, a common value for TTS. Time steps is derived from the token IDs, count, often a multiple of the token count because one phoneme typically spans multiple time frames in a spectrogram. This mock tensor represents the output that a real acoustic model would produce, ready for the next stage. Here, we fill our mock MEL spectrogram with dummy data. We're creating a simple sine wave pattern. While this is purely illustrative and doesn't represent actual speech, it demonstrates the structure of the MEL spectrogram, a 3D array where each element, batch, mel_channel, time_step, holds a float value representing the energy at a particular frequency band at a specific point in time. In a real model, these values would be highly complex, learned features that encode the spectral characteristics of the desired speech. Moving to run vocoder, we again see the commented out ONNX model loading at line 93. Just like the acoustic model, a real vocoder would be loaded as an inference session from its ONNX file, e.g., vocoder.onx. The vocoder's job is to take the MEL spectrogram, which is a compressed, frequency domain representation, and reconstruct the high-fidelity, time-domain audio waveform. This is a computationally intensive task, often involving generative adversarial networks, GANs, or autoregressive models. We define the time steps from the input MEL spectrogram and then calculate audio length. The audio length is significantly larger than time steps because vocoders perform an upsampling process. For instance, if a MEL spectrogram frame represents 10 milliseconds of audio, and the audio sample rate is 16 kHz, then 10 milliseconds means 160 samples. A common upsampling factor like 256 means each MEL spectrogram time step expands into 256 audio samples. This expansion is how the vocoder generates the fine-grained detail of the audio waveform from the coarser MEL spectrogram features. This loop generates our dummy audio waveform. We're creating another sine wave, but critically, its amplitude is modulated by the MEL spectrogram features. This is a simplified representation of what a real vocoder does. It uses the spectral information from the MEL spectrogram to guide the generation of the raw audio samples. The I%80 and I/256 are crude ways to map the high-resolution audio samples back to the lower-resolution MEL spectrogram features. A real vocoder would use sophisticated neural network layers, like convolutions and upsampling, to achieve this transformation smoothly and realistically. Finally, the save audio to file method is a placeholder. It simply prints a message indicating that audio data would be written. In a real application, you would use a dedicated audio library like InAudio or System, Media, Wave for C# to construct a proper wave file. This involves writing a header that specifies parameters like sample rate, number of channels, and bit depth, followed by the actual float, audio samples, potentially converted to a specific integer format, e.g., 16-bit PCM. This step is crucial for making the synthesized speech audible and shareable. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. This lesson is excerpted from Volume 9, Chapter 14 of the C# and AI Masterclass ebook series and from the volume Edge AI and Local Inference. Running LLMs, Llama/Phi, locally with C# and ONNX. You can find all source code here, https://github.com/edgarmilvis/C# programming series. The ebook includes 20 chapters, each one with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. Thank you for your attention. I look forward to seeing you in the next lesson.